This is lecture 8, dual theory for IE 3340, operational research. So in this slide, I want to just show you the progress that we have made so far in this semester and connecting the topics that we have covered so far with the course objectives. And as you can see, this map is showing you how the topics on the right, how the topics that we have covered are aligned. So far until previous lecture, we covered sensitivity analysis. So sensitivity analysis and dual theory are related. The idea still is to gather insights from the solution of the problem. During the sensitivity analysis lecture, we learned about the shadow price, the reduced cost, and so on. And we learn how to use that information to answer questions that are relevant from a managerial point of view. And we're going to extend that analysis today with this lecture. So the last few lectures are connected to the solve the models for the optimal solutions course objectives. And also the lecture that we are going to discuss today is connected to the objective that states that you need to learn to interpret the model solutions and infer solutions to the real world problems. So that's the extra box and connection to sensitivity analysis and dual theory. So the learning objectives for this lecture is to understand the concept of duality. And also we want to explain how to use the solution of the dual problem, which we are going to explain today in sensitivity analysis. So the agenda for this lecture is to define what is the dual problem. And also we want to identify relationship between what we're going to call the primal problem and the dual problem that we're going to define today. The primal problem is basically the original formulation, the original linear program model that you formulate to solve a problem. So that's what we're going to call the primal. And from the primal, we are going to define the dual. So we want to understand the relationships between them. Also, as part of this lecture, we're going to study the economic interpretation of duality and the post-optimal analysis. So let's start with the definition of the dual problem. So the dual problem is defined systematically from the primal or the original linear programming model. So basically, you are given a problem, you understand that linear programming is a tool that you can use to solve that problem, and you formulate the problem for, you formulate the model for that problem. That's what we're going to call the primal. So the dual is defined systematically from that original model. The two problems are closely related. The optimal solution of one problem automatically provides the optimal solution to the other. Okay, so these two models, primal and the dual, will have the same optimal solution. Our definition of the dual problem requires expressing the primal problem in the equation form or the standard form that we discussed in previous lectures. So let's see how can we build or define this dual or the dual problem. The key ideas for constructing the dual from the primal are summarized as follows. So first, we are going to assign a dual variable for each primal equality constraint. So if you have 5 constraints in your problem, then you're going to assign one dual variable to each one of the constraints of the problem. So 5 total. Then we're going to construct a dual constraint from each primal variable. Okay, so how are we going to do that? The column constraint coefficients and the objective coefficient of the j primal variable, respectively, define the left hand and the right hand side of the j dual constraint. So basically, if you have x1 defining variable for your primal model, let's say x1 shows in the first constraint, the second constraint, the third constraint. So that's going to form a column. So this is what I'm referring to. So you have x1. Let's say this is constraint 1. So x1 shows up here. Constraint 2, x1 shows here. So you have plus. In constraint number 3, x shows up also. So the idea, and then you have the objective function that also has, let's say, maximize x1 plus. So this information, the coefficients associated with those x1 values are going to define a constraint for the dual problem. So the objective coefficient of the j primary variable respectively define the left hand and the right hand side of the j dual constraint. The dual objective coefficients equal the right hand sides of the primal constraint equations. And we're going to show some examples. So this is going to make more sense in a second. The sense of optimization, direction of inequalities, and the signs of the variables in the dual are governed by the rules in the table. Okay, so let's say that the original model, that primal model, is a maximization. In the dual, or for the dual, the objective function is going to be minimization. And then the constraint type is going to be greater or equal to, and the variable signs are going to be unrestricted. If you have a minimization problem as your original problem, then the objective function for your problem in the dual is going to be a maximization, and the constraint type are going to be less than or equal to with unrestricted variable sign. So let's look at one example. So example 1, you have a maximize z that is equal to 5x1 plus 12x2 plus 4x3. And then you have 2 constraints, x1 plus 2x2 plus x3 less than or equal to 10. 2x1 minus x2 plus 3x3 equals 8. So the first thing we have to do is to set up this problem into the standard form or the equality form. So as you can see, we have an inequality here. So we need to make that an equality. So what we do is we add this additional slack variable. So in this case, instead of using s, I'm using x4 to make this an equality. So x4 is a slack variable in this case. So it's showing up in the objective function as 0 with a 0 coefficient. So basically, it's not making any difference in the objective function. And then for the second constraint, we don't have to do anything because that's already a equality. So the second constraint is the same. So as mentioned earlier, we are going to assign a dual variable to each one of the constraints. So y1 is going to be associated to the first constraint, and y2 is going to be associated to the second constraint. So using this information, we're going to define the dual problem for this primal. Okay, so as mentioned earlier, since this is a maximization problem, the dual problem is going to be a minimization problem. So we are going to minimize. And instead of Z, we're going to use W just for identifying the dual problem. So for the coefficients of the objective function, we are going to use the right-hand side coefficients of the constraint. So it's going to be 10 times y1, since 10 is associated to the first constraint, and plus 8 times y2, because 8 is associated to the second constraint. So we define a dual variable for each one of the constraints, and then we're going to use the coefficients of each constraint to define the objective function, in this case, using the right-hand side of each one of the constraints. So we are going to multiply the right-hand side times the dual variable associated with that constraint. So for the first constraint, 10 times y1. For the second constraint, 8 times y2. So that's the objective function. Now, in terms of the constraints, it's going to be subject to, as mentioned earlier, we are going to use for each one of the variables in the primal. So we have x1, we have x2, which has a negative coefficient, and we have x3, and we also have x4. Okay, so we are going to define a constraint for each one of the variables in the primal. Okay, so we start with the x1 in the primal, and we are going to look at the coefficients here. The first coefficient here is a 1. 1 is associated to x1. So it's going to be 1 times y1. So it's 1, y1. And then the coefficient for the second constraint is 2. So it's 2 plus 2, y2. Okay, so as mentioned earlier, since you're going from maximization to minimization, the constraints are going to be greater or equal to. And the right-hand side of the constraint is going to be the coefficient in the objective function. So this is 5. And we're going to repeat the process. So for the second variable, we're going to define the second constraint based on the second variable, x2. So this coefficient is -1. So don't forget that. So we have 2 times y1 minus 1 times y2 greater or equal to 12. And then we have for x3, we have coefficient 1 and coefficient 3. So we have 1 y1 plus 3 y2 greater or equal to 4. And then we have the last one. We have a 1 here, y1 plus 0 y2 greater or equal to 0. And as we mentioned earlier, y1 and y2 will be unrestricted in sign. And that's based on this information that I show you here. Right, so for maximization, the objective of the dual is going to be minimization, the constraint is going to be greater or equal to, and the variable sign is going to be unrestricted. But as you can see by this constraint, we are forcing y1 to be greater or equal to 0. Okay, so that's the first example. We have a second example here for a minimization problem. So it's the same idea. We want to minimize z equals 15 x1 plus 12x2 subject to x1 plus 2x2 greater or equal to 3, 2x1 minus 4x2 less than or equal to 5, and then x1, x2 will be greater or equal to 0. So the first thing we have to do is to set up this into the equation form. So that's what we are doing here. So this is the standard form, both constraints in equation form. So for the first one, we need to add a excess or subtract an excess variable. And for the second one, we have to add a slack variable. And those two are showing up here as well. So that is the equation form. So we proceed as we did for the previous problem, with the only difference that now we have a minimization problem. So what that means is that our objective function for the dual problem is going to be a maximization, maximize W. And again, we look at the right-hand side of the constraints to find the coefficients for the objective function. So it's going to be 3y1 plus 5y2. So that's the objective function for this problem. And then this is going to be subject to, again, we look at the coefficients for each one of the decision variables of the primal. And then we're going to use those coefficients to define our constraints. So here we have this, and here. So for the first one, we have y1 plus 2y2. And since we are going from minimize to maximize, then the constraints are going to be less than or equal to 15. And then for the second variable, x2, we have 2y1 minus 4y2 less than or equal to 12. And for the third constraint, we have minus y1 plus 0y2 less than or equal to 0. And for the x4, we have 1y2 less than or equal to 0. And again, y1 and y2 are unrestricted in sign. We have one example, an additional example. Example 3, we start with a unrestricted x1 variable. So we need to perform, you remember, substitution that we discussed earlier in the semester. That substitution right there for unrestricted variables. So we do that for this particular problem. So we have x1 is going to be equal to x1 minus and x1 plus. So let's proceed. So again, we go from maximization to minimization. But remember, first thing we do is to make sure that all the constraints are in equality form. So we are going to start with making those constraints that are not equalities. We're going to make them equalities by using the slack variables and the excess variables. Okay, so that's what we're doing here. We don't have to do, so remember we are substituting x1 by this. So everywhere that you see x1, that's what you're going to see now. And then for the first constraint, we don't need to do anything. For the second constraint, we are subtracting this x3, x's variable. And for the third constraint, we're adding that slack variable. And we also have a variable assigned to each one of the constraints. So a dual variable for each one of the constraints. So let's show the dual problem. We are going to minimize W, which is going to be equal to 5 times y1 plus 3 times y2 plus 8 times y3. And we're going to have a constraint again for each one of the variables. So we're going to have this. And you know the process now. So we're going to start with that, the coefficients for x1 minus. So this is going to look like this. So this coefficient times y1 is 1, y1 minus y2 plus 4, y3 and greater or equal to 5, which is the coefficient for the first variable in the objective function of the primal. And then we have minus y1 plus y2 minus 4 y3 greater or equal to minus 5. And then we have 2y1 plus 5 y2 plus 7 y3 greater or equal to 6. 6 is coming from here. And then we have minus y2 greater or equal to 0 and y3 greater or equal to 0. And we also have y1, y2, and y3 unrestricted inside. But you know some of these constraints are going to impose some of those signs, okay? So those are the 3 examples. These are the summary of the rules. It's a little bit more elaborated if you compare this table with table 1. So from maximization, if you have these constraints, these are how the variables are going to be impacted. And this is how your variables are going to impact the constraint of the other problem. Same thing goes from minimization to maximization. I think it's easier to just to follow this table. It's easier to remember. So if the primal is maximization, then the dual is a minimization problem, and vice versa. Okay, so let's talk about some of the primal dual relationships. Changes made in the data of a linear programming model can affect the optimality and or the feasibility of the current optimal solution. This section discusses primal dual relationships that can be used to recompute the elements of the optimal simplex tableau. These relationships form the basis for the economic interpretation of the linear programming model and for post-optimality analysis. So let's go back to the simplex tableau layout. The figure represents the starting and general simplex tableau schematically. So this is our starting tableau, and this is the general tableau. Okay, so starting in general. So general means that after some iterations. In the starting tableau, the constraint coefficients under the starting variables form an identity matrix, right? We remember that from our discussion of the simplex method. Our initial solution and the basic variables always, when you put them together, if you put together those columns, they're going to form the identity matrix. Subsequent iterations of the simplex tableau generated by the Gauss-Jordan row operations modify the elements of the identity matrix, that original identity matrix. After a couple of iterations, those coefficients are now different. The inverse matrix is key to computing the, so the when you those elements that are modified, modify the elements of the identity matrix to produce what is known as the inverse. Okay, so if we follow this after each iteration, if we keep following that initial, the area where the initial solution was or the starting variables were, then that area is going to provide us with the identity matrix. I'm sorry, with the inverse matrix. The inverse matrix is key to computing all the elements of the associated simplex tableau. So the optimal dual solution. The primal and dual solutions are closely related. The optimal solution of either problem yields the optimal solution to the other. In an LP model in which the number of variables is considerably smaller than the number of constraints, computational savings may be realized by solving the dual. Why is that the case? The amount of simplex computations depend largely on the number of constraints. So the idea behind, in addition to gather insights from the solution of the problem, the dual also can help you solve the problem faster by providing you with a new framework for the problem and also a different number of constraints and variables. So if you're looking at minimizing the number of simplex computations, then that will depend on largely on the number of constraints. So if by formulating the dual, you can reduce the number of constraints, that means that you can solve the problem faster. So in terms of the dual solution, this section provides two methods for determining the dual values. So meaning that if you had the optimal solution for the original problem, and you want to find the optimal solution for the dual, meaning those y1, y2, y3 variables, then you have two methods in which you can obtain that solution. In method one, the optimal value of the dual variable, y1 or yi, is going to be equal to the optimal primal z coefficients of the starting variable xi plus the original objective coefficient of xi. In the second method, the optimal values of the dual variables is going to be equal to the row vector of the original objective coefficients of the optimal primal basic variables times the optimal primal inverse. The elements of the row vector must appear in the same order the basic variables are listed in the basic column of the simplex tableau. And that's a very important observation, because if you don't get the right order, then the solution that you're going to obtain is not going to be right. So let's look at one example. So again, we want to use the dual. We want to find the optimal solution for the dual given the primal. So in this example, we are going to use artificial variables. So we are maximizing, this is the primal. So we're using the M method and we are using an artificial variable here. So if we formulate the dual for this problem, dual is gonna look as follows. So minimization of W equals 10y1 plus 8y2 subject to y1 plus 2y2 greater or equal to 5, 2y1 minus y2 greater or equal to 12, y1 plus 3y2 greater or equal to 4, and y1 greater or equal to 0, and y2 greater or equal to minus m. So let me fix this quickly so it looks better. Should be y2. So we have the dual based on the primal. So here's the optimal primal optimal tableau. So this is after applying the M method. This is the optimal solution for the problem. And you can find in that shaded area, this is the location of the initial or the starting solution for the problem. So that's important because there's some information that's gonna help us find the optimal solution for the dual. So the optimal solution for the primal is given in here. This is the optimal solution. The optimal, I'm sorry, do this again. So this is the solution, the optimal, the objective function solution. And what this is saying is that x2 is going to be equal to 12 over 5, and x1 is going to be equal to 26 over 5. So what we want to find now is, okay, we know the dual problem now. This is our dual. So we want to use one of the two methods to find what's the value for y1 and what is the value for y2. So let's do that. So we are going to use the starting primal basic variables for method 1. So the starting primal basic variables were x4 and r. So those are the ones that we are using here. And we're going to take the z equation coefficients from the optimal tableau. So in this case, it's 29 over 5. And in this case, it's going to be minus 2 over 5 plus m. We also need the original objective coefficient for this problem. So if we go back to the original problem, what were the coefficients for x4? So x4 is not showing up in the objective function. So the original coefficient for x4 will be 0. And in the original problem, the coefficient for r was minus m. So minus m. And the dual variables associated are y1 and y2. And what are the optimal dual values? Well, we're going to use this information to find out. We're going to use this, and we're going to use that. So let me use a different color. So in this case, it's going to be 29 by 5 plus 0, which is going to be 29/5. And in this case, it's going to be minus 2/5 plus m minus m, which is equal to minus 2/5. So I'm using method 1, which was described here. Okay, so that's the method that I'm using. And using that method, I can find the value for y1 and y2. So y1 equals 29/5 and y2 equals minus 2/5. We can also use the second method, and we will arrive to the same result. So the optimal inverse matrix highlighted in the tableau under the starting variables x4 and r is the following. This is the matrix: 2/5, 1/5, minus 1/5, and 2/5. So that's coming from here. The order of the optimal primal basic variable in the basic column is x2 followed by x1. So the order of the optimal primal basic variable in the basic column is x2 followed by x1. So this is what we are referring to, x2 followed by x1. The elements of the optimal the original objective coefficients must appear in the same order. So must appear in the same order. So the original objective coefficients will be equal to coefficient sorry. Let me write this more clear. Coefficient of x2 and then coefficient of x1. So in this case, that will be coefficient of x2 is 12, and then the coefficient of x1 is 5. So this is 12 and 5. So the optimal dual values are the following. Y1, Y2 equals the original objective coefficients of x2, x1 times the optimal inverse. So this is going to be equal to 12 and 5 times 2 over 5 minus 1 over 5, 1 over 5, and 2 over 5. So this is going to be equal to 29 over 5 minus 2 over 5, which is the same solution that we found using the first method. So as you can see, following either of the methods, you will get the same answer. Okay, so what I just showed you are two methods in which you can find the optimal solution for the dual using the primal optimal solution. The primal dual objective values for any pair of feasible primal and dual solutions, the objective value in the problem, in the maximization problem, is always less than or equal to the objective value in the minimization problem. At the optimum, the relationship holds as a strict equation, meaning that the two objective values are equal. So if you use, and I'm going to let you do that on your own, if you take the values of the dual, let's say 25 over 5 and minus 2 over 5, and you plug that into here, into the objective function for the dual, you should get this same solution, 54 and 4 over 5. So you can try that. Okay, so I'm going to stop here and we'll continue in the next video.